So the solution of optimization problems is quite similar to the solution of equations. They follow the same rule. First, to define the unknown vector, and then rewrite the objective function, and then you have to call administer or other functions. And if you call the function where three variables are returned, the third variable will tell you whether the optimization process is successful or not. In fact, we can return four variables. Like this. Oh, in fact, this one is not considered successful because there is a warning. Using line search cannot find the points. Maybe we have to modify the method. I will explain later to you how to modify the method or algorithm. Actually, this result is good enough. This is the objective function, and the last argument returned is the C, which returns this information. First, how many iterations used? So this one would be used 9 iterations to solve this. And the objective function number, code numbers of objective function is 33. And the algorithm, we can display the algorithm. C dot algorithm, which will display something like this, and C dot message will display the error information like this. That is that the standard line search method cannot find accessible points. So the value of B, the second argument, is a negative value. And now let's see this example. Let's draw this curve. Again, actually I have already drawn this curve before. We can draw this curve again and show the idea of global minimum or local minimum. Well, I have to use easy plot to draw the curve. I can only specify a certain means, for instance, -3 to 2. And in this area, we may see that actually the global minimum is not displayed. It should be something around here. But using search method, if we select a initial point from here, then it may find the local minimum point, find this point rather than the global minimum point. So sometimes the optimization problems using search method may fail. And I will explain later on what method should we use other than the search method to find a global minimum later. So this is the idea of local minimums and global minimums. And all these points might be searched, might be found, but these are the local minimums which are not useful. What we are interested in is the global minimum. And the next topic is how to improve the accuracy of solving optimization problems. In this case, I have to describe the use of gradient information. And first, I shall explain or demonstrate an example for you. Suppose we want to find the minimum value of this function. If you solve this problem by hand, you will notice that these two terms are non-negative. So the minimum value of this function is to let this one be 0, which means x1 equals to 1. And also we want this one 0. To substitute x1 equals to 0, we have x2 equals to 1. So the global minimum point is 1, 1. So now let's check whether the unconstrained optimization problems can find the global minimum point. To solve this problem, what we need to do is first to describe the function, objective function. And then we can give specifications on the accuracy. And then we can call the f-min UNC function to solve the problem. It seems to be 1. However, if we display more points, more number, more digits, what we find is a result like this. And the result will never go to 1 because there are errors. No matter how accurately we set the criterion, we set TOLX equals to 10 to the minus 10, we cannot reach that specification. So how can we improve the accuracy of the solution? Before that, I will first draw the objective function as contours. And this is the contour representation of the original objective function, and it is found that the optimal solution is here. This part is quite flat. Normally you cannot approach this point actually because the objective function will not change much for the variation of x. And this function is also known as the banana function because this one looks like a banana. It is proposed by a famous professor, Rosenrock. I think some of you may have already heard that name. In multivariable control system design, very influential professor. So for this kind of objective functions, for this objective function, the objective function itself may not provide necessary or adequate information on the optimization process. Apart from that, what we need is the gradient, the derivative of the objective function with respect to x1 and x2. We need that information also. So we can find the gradient of the original function easily by symbolic computation like this. That is the Jacobian matrix from f to x1 and x2. We can find the information.